magnets from X, your favorite alien. Now this is one of the most important videos in the entire series, because we are about to see that all the shapes we traced with the Hall effect sensor are not just shapes. They are, in fact, the real interactions taking place between magnets. In other words, when we use a Hall sensor to map those geometries around a magnet, it's essentially the same as using another magnet to interact with it, always through those very same forms. But this only works if we respect the exact same measurement angle we use during the sensor analysis. Before diving into this, I want to dedicate a few words to possible errors you might encounter, especially when working with sensors. If we want to compare these figures to the results of equations, which as you know are nothing but numbers in an ideal world, then here in the real world, we must account for every problem and every possible solution. Aside from the intrinsic properties of the magnet itself and various external influences we already discussed in earlier videos, there's another critical factor: the sensor you are using. Take a look at this. Here we have a measurement taken perpendicular to the magnetization axis, producing this three-dimensional shape, another kind of d orbital. But in this case, notice how this bubble here is smaller. When we use a different sensor, however, we immediately see that the problem wasn't the magnet at all. It was the sensor itself. And the discrepancy can reach up to a full centimeter between the two. This is why it's absolutely essential to check your measurements carefully, and whenever possible, compare results using multiple sensors to make sure the shapes are correctly identified. But, as I was saying earlier, there's also another method that can reveal whether your measurements are accurate. Let's begin by testing the very shape we use to explain the method, which, I'll admit, is pretty wild. And let's see if it really corresponds to how magnets actually interact with each other. For accurate measurements, you can always go back to the earlier videos. For now, we'll take a more hands-on approach. No rulers, no strict geometry, just to show you a few more things. Alright, now we have this figure, a section of the classic d orbital with two lobes and a central donut. But what exactly is this figure? What is it supposed to represent? To find out, Marsio built a very simple, almost primitive device. And yet, it's capable of testing the authenticity of these shapes. Here it is. It's nothing more than the transparent casing of an ordinary ballpoint pen. Remove the ink tube, and inside you insert cylindrical magnets. Once the magnets are in place, you use a lighter to seal the two ends. This little tool will allow you to test the shape of the detected magnetic field, depending on the orientation of your observation. In other words, it lets you preserve a precise angle of interaction with simple magnets, just as the Hall sensor does. To build it properly, you'll need to match the strength of the cylindrical magnets to the strength of the sensor's measurements. To do that, I recommend testing against a bubble of opposite polarity. Check whether the magnets are repelled before or after the perimeter traced by the sensor. Based on that, you can add or remove magnets inside the pen until the interaction matches. Since it's easier to test shapes using repulsion rather than attraction, let's slowly approach all the repulsive regions with our pen and check whether the magnets obey the predicted geometry of interaction. And yes, it seems they do, don't you think? And for the ultimate proof test, watch what happens if we use the pen at a perpendicular angle different from the one used during the measurement, which was parallel to the magnetization axis. Everything collapses, the geometry is lost, and we can no longer identify where or how the magnets will react. So now let's actually construct the map taken perpendicular to the axis and use it to test another shape, this one here. Once again, we can clearly see that all the interactions are respected. I'd like to remind you not to think of these bubbles as mere polarities, but as interactions. So even if you see, for example, a red area repelling the blue tip of the pen, the true interpretation is different. And that's something I explained in detail in the previous video. Continuing with the very same magnets under analysis, but this time with a different measurement method, the full 360-degree detection, we get yet another shape, the p orbital. I'll speed up this part just a little, but it's important that you see how it's done. You need to trace every measurement point, always pointing the sensor directly toward the magnet, both for the outer and inner regions, exactly as you see here. The resulting 3D shape is precisely that of the corresponding orbital. In this case, the magnets are rectangular, so the form appears a bit elongated, but the orbital structure remains unmistakable. Now we can also test this new map. But this time, the orientation of the magnet must be handled in a full 360 degrees, just as we did with the sensor. And here too, we can confirm. Everything matches perfectly. But to be absolutely certain that this verification method works, Marsio carried out a far more complex detection. In this case, we have three magnetic blocks, placed randomly, aligned in attraction with each other, a configuration so unusual that not even he had ever attempted it before. And unlike the previous shapes you've seen, here we had no idea what the resulting figure would look like. So let's speed things up a little, so you can watch the entire process unfold. Here we go. the result is a truly unusual, unexpected shape. Yet even here, by testing each of the detected magnetic bubbles with another magnet, and keeping the same measurement angle, we find that every interaction is faithfully reproduced, even the strangest and most intricate ones, right in the center of those three magnets. So what does all of this tell us? It confirms that the shapes revealed by the Hall sensor are not meaningless images. They are, in fact, the real interactions that develop between magnets. And through these shapes, we can actually predict what will happen, whether we are dealing with a single magnet under analysis or with a complex magnetic system. And now I want to ask you, do you know what else uses these same shapes and in the very same way predicts interactions? Exactly, atomic orbitals. They share the same geometries, the same functions. Is it just a coincidence?